We will now go over the solutions for practice quiz number 6. Let's start with the first problem. The moons of Jupiter, discovered by Galileo, were the first moons found orbiting other planets. Jupiter's moon, Alethea, has a mass of 2.08 times 10 to the 18th kilograms and orbits Jupiter at a distance of 1.81 times 10 to the 8th meters. What is the magnitude of the gravitational force between Jupiter and Alethea? The mass of Jupiter is 1.90 times 10 to the 27 kilograms. Okay, the magnitude of the gravitational force is G, capital G, times m1 times m2 divided by the distance squared between the two masses. G is 6.67 times 10 to the negative 11th. The first mass, let's take the Jupiter first, 1.90 times 10 to the 27th. The order obviously doesn't matter. The second mass we'll take to be Alethea, the moon, 2.08 times 10 to the 18th. The distance between is 1.81 times 10 to the 8th. We square that. Everything is in their proper units. Kilograms is a standard unit. Meters is a standard unit. Okay, and you plug into your calculator and it becomes 8.05 times 10 to the 18th newtons. Next question. Suppose a new extrasolar planet is discovered. Its mass is double the mass of the Earth, but it has the same density and spherical shape as Earth. How would the weight of an object at the new planet's surface differ from its weight on Earth? Okay, so they want to know what is the force on this mass at the surface of the new planet versus the force on the mass at the surface of Earth. So let's say P is for planet, E is for Earth. Okay, they tell you that the mass of the planet is twice that of Earth, so I write down MP is equal to 2ME. Right? So this problem to me is straightforward, except maybe the whole issue about the densities are the same and has the same spherical shape. This is a little bit complicated. This part here is how we get the relation between the radius of the planet and the radius of Earth. But except for this step here, the rest I'm going to try to convince you should be something you can do straightforwardly. Okay, so let me actually start there. So whenever you have a problem where you are said, here's how things are on Earth or some given planet, and then here are how things are on another planet, and you want to know what is the relationship between the force on this planet versus, let's say, Earth. Okay, you just first you should use a good notation. We'll use E for Earth, use P for planets, and label everything. Don't use the same symbols for the stuff on Earth and the stuff on the planet, because then you'll have very strange equations like m is equal to 2m, which doesn't make any sense. You need to label things out properly. Okay, that's the first key thing I want to mention. All right, now the next thing you do is you then take, let's say, the second expression, and you write the quantities with these labels in terms of the information that's given in the problem. For example, the mass of the planet is twice that of the mass of the Earth. Okay, and then we're going to try to write the radius of the planet in terms of the radius of the Earth. It turns out to be 2 to the 1/3 power times the radius of the Earth. Let's just skip for the moment how we got that. But after we plug that in here, we end up with G ME times M divided by RE squared. That's equal to the, by the way, this term here is the force on the mass at the surface of the Earth. You recognize this is exactly after that. All the extra stuff is there's a factor of 2 here, there's a factor of 2 to the 2/3, and that cancels out to give 2 to the 1/3, which is 1.26. So the force on the mass at the surface of the planet P is 1.26 times the force of the mass at the surface of the Earth. Okay, so just to review, we write down the force for the mass at the surface of the Earth, the surface of the planet, and then you convert everything with p's in terms of m's from the information in the problem, and then you get that it's 1.26 times the force on the surface of the Earth. Now the one maybe tricky step that maybe you're not familiar how to do this is slightly more complicated, is they tell you that the densities are the same. Okay, if the densities are the same, so density is mass per unit volume, and the planet P has twice the mass of Earth, then the volume of P must be twice the volume of E. Okay, if the densities are the same, you need twice as much volume for P to have twice as much mass. Now, because the volume is proportional to radius to the third power, in fact, the formula for the volume of a sphere, the volume of the sphere is 4/3 pi r cubed, if you were wondering about that. But the main point is it's proportional to the radius to the third power. Okay, since volume is proportional to the radius to the third power, that means rp cubed, which is proportional to volume, is equal to, because it's twice the volume of that on Earth, it must be 2 times RE cubed. Okay, because Vp is equal to 2VE, that means Rp to the third power is equal to 2RE to the third power. Now then we can solve by taking the cube root of both sides. We get Rp is 2 to the 1/3 power times Re. Okay, so this step maybe is a little bit complicated, but the rest here hopefully you can get. Right? And that's how we get Rp is equal to 2 to the 1/3 power, and that's what we substitute in here. Let's go on. A planet is in a circular orbit about the Sun. Use Newton's law of gravity and his second law of motion to calculate the period of the planet measured in days. The data is that the mass of the Sun is 1.99 times 10 to the 30 kilograms. The mass of the planet is 6 times 10 to the 24 kilograms. The radius of the orbit is 1.496 times 10 to the 11 meters. Okay. So the formula for the orbit, the speed of orbit is the square root of g times m over small r. That's on your equation sheet. If you're wondering how that gets derived, if you want to make sure you understand the underlying physics, maybe they ask you a more detailed question about the orbit of a satellite. The way we do that, remember how it goes? We have a satellite out here. Here's, let's say it's, this is the Sun, but in this case, the satellite will be a planet. Okay, so some radius here, and then we have a centripetal force. It's mv squared over r. But this centripetal force is provided by gravity, and so that has a value of the force is capital G, capital M times small m over r squared. So gravity is providing the centripetal force. What we do is we cancel the one factor of r, then we cancel out the m. We get v is the square root of g m over r. You see, it only takes a couple lines to derive this. That's the speed of this satellite going around in an orbit. Okay? So we plug in the values. G, capital G, 6.67 times 10 to the negative 11. Capital M, the mass of the Sun, is 1.99 times 10 to the 30. The radius is the distance from the Sun to the planet is 1.496 times 10 to the 11. We use small r for lots of things, but typically when it's just plain old r without a subscript, like e or something like that, it's the distance between the two objects, from the center of one object to the center of another object. Small plain r with no subscript means that distance. We punch this into our calculator with the square root here, and we get 29,800 seconds. Okay, sorry. 29,800 meters per second. So I'll fix that in my solutions here. Now then what we want to do is we want to get the period. The period, to calculate the period, we first calculate what is the distance to go around one time. The distance to go around one time is 2 pi r, that's the circumference. Okay, and we divide by the speed. We divide distance by speed, we get time. Distance divided by speed equals time. And so we have 2 pi times 1.496 times 10 to the 11th, that's the radius of the orbit, divided by the speed, 29,800. and we get 3.15 times 10 to the 7th seconds. But they wanted the answer in days. 1 second is 1 over 24 for hours in a day, divided by 3,600 for the number of seconds per hour. So it's 1 over 24 times 3,600 as a fraction of the day, 1 day. So we divide the 24 and 3,600, and we get 365 days. Clearly that's equivalent to what's happening with the Earth. So it's that this happens to be the radius that the Earth is at for this for physical value of the Sun, its mass. Okay, next problem. Eris, the largest known dwarf planet in the solar system, has a radius r, capital R, 1,200 kilometers, and an acceleration due to gravity on its surface of small g is equal to 0.77 meters per second squared. Okay, use these numbers to calculate the escape speed from the surface of Eris. Okay, so the formula for the escape speed of a starting from the surface of the Earth, or surface of any planet, is square root of 2g mp over rp. Okay, that's the radius of the surface of the planet. If you're wondering how that's derived, basically what you need is, here's the surface of the planet. Okay, you're at some radius rp, and the potential energy is minus the mass of the planet times the mass of your object. So this whole thing has a mass of mp over rp. Okay, and what you need is you need the kinetic energy to be equal to positive g mpm over rp. Okay, if that's equal to the positive value of this, then k plus u, the total mechanical energy, will be equal to 0. Okay, and then you have enough energy to escape. It can go to outer space. Now, if you set this equal to 1/2 mv squared, okay, then we have 2 mpm rp is equal to 1/2 mv squared times 2. Cancel the m, and we get v for the escape is equal to square root of 2 gmp rp. Okay, I'm just showing you this to remind you where it came from, but this equation is on your equation sheet. Okay, I'm hoping by doing this derivation it helps stick in your mind a little better. Okay, so if we knew mp, the mass of the dwarf planet Eris, and the radius, which we're actually given, then we can calculate the escape. But they don't give us mp, so we're kind of stuck here. So we have to figure out mp, the mass of Eris. But they do give us small gp, which is the acceleration due to Eris at the surface of Eris. So gp, small gp, the idea is if we're on the surface of Eris, then the force of gravity will be equal to the mass of the object times gp, small gp. Okay, just like on the surface of the Earth. But this must be equal to the universal formula, capital G mp times small m over rp squared, because the distance between these two is equal to rp, the radius of the planet. Okay, so now to get small gp, by the way, these formulas both are on the equation sheet. It's actually written this way: mg, small m, m times small g is equal to capital G times capital M times small m divided by r squared. So then we can cancel out the m's here in this equation, and we get that it's just capital G times the mass of the planet divided by the radius of the planet squared. Okay, that's what I have here. We're going to say small gp is equal to capital G times mass of the planet divided by the radius of the planet squared. If 0.77 is equal to 6.67 times 10 to the negative 11 times mp, which we don't know, divided by the radius, which is 1,200 kilometers, so multiplied by 1,000 to make it into meters. That has to be squared. and we get MP is equal to 1.66 times 10 to the 22 kilograms. Now we have the mass of the planet. We can just plug it into our escape velocity formula, which is in the equation sheet. So we take the square root of 2 times g, 6.67 times 10 to the negative 11, times the mass of the planet, which is 1.66 times 10 to the 22, which we've got here. We divide by the radius here, RP, so 1,000, so radius is up here, 1,200 times 1,000 for converting from kilometers to meters, and we get 1,360 meters per second. Okay, there is a quick and dirty way of getting this much more quickly. We use the fact that small g of p, small g subscript p, is capital G mp divided by rp squared, and the escape velocity is the square root of 2 capital G mp divided by rp. And then we'll notice that these are the stuff inside the square root is very similar to that formula for small gp. If I just take 2 times small gp, I get almost what I need, but then I need to get rid of this rp squared and convert it to just rp to the first power. So if I multiply by rp, this will be exactly my formula for the escape speed. So now I can have the square root of 2 times small gp times rp, and that comes out to 1,360 meters per second. Okay, let's go on. This is a graphing problem. So you should know how to read these graphs, how to draw a graph of the oscillating simple harmonic motion, and how to read off the various elements in this graph. Okay, first of all, amplitude is the highest point, okay, of the graph. The period is how long it takes to go from one point to the repeat point, the shortest, nearest repeat point. So going from here to there, or here to there, it doesn't matter. Okay, other things they want to know, let's read the problem. So the position versus time graph of the mass on a horizontal spring is shown in the figure, with positive and negative x corresponding to right and left as usual. What can you say about the velocity of the mass and the force acting on the mass at the instant indicated by the dashed line right here at this time? So at this point here, notice that the slope of the curve is 0, so that means that the velocity, which is proportional to the slope, the instantaneous velocity must be 0. Now, notice that the slope is increasing. It used to be negative, then less negative, then 0, and then positive and increasing. Okay? If it's increasing, that means that the acceleration is positive, so the force, which is proportional to the acceleration, force is equal to mass times the acceleration. This is pointing to the right. Okay, we can do this without all this math, though. Easier solution using physics. So the mass here at this time is at negative a, so it's oscillating like this. So at negative a, it's way over here to the leftmost point. So it's at the leftmost point. All right. The spring must then, if it's at the leftmost point, must be trying to pull it to the right. So the force is to the right. And at the leftmost point, it's at an extreme value, so it's turning around, and the velocity is momentarily 0. So that's how we can figure out the velocity is 0, the force is to the right. Let's go on. To take the place of shock absorbers, a go-kart has a spring on each wheel with K spring constant equals to 550 newtons per meter, including the passenger. The weight of the vehicle is 105 kilograms. What would be the period of oscillation of the car in seconds if it were to hit a rock or pothole? Okay, so a go-kart, it should be stated in the problem for those who don't know what a go-kart is. It's just a little kiddie car, a car for kids that has 4 vehicles for stability. Okay, four wheels. And so you have 4 springs, 1 for each wheel. Now, notice that when you have 4 springs that are supporting the car, they work in concert with each other, and together they produce 4 times as much force for a given displacement of each spring. Okay, so the spring constant for all 4 forces together, all springs together, as one big effective spring would be K all. It's called all for all springs is equal to 4 times K. So the whole point is we have 4 springs. Think of it like this. They all work together. So if I extend it by amount x, then we have 4 times the force. So this for all is equal to 4 times the force for one spring. So as a result, the K value, the spring constant, will be 4 times the value of the spring constant for 1. Okay, so we have 4 times K, so that's 4 times 550, that's 2,200 newtons per meter. Now we have a formula that the period is 2 pi square root of m over k all. Well, the k for the spring, in this case there's an effective spring for all 4 of them. So it's 2 pi times the square root of 105 divided by 2,200, you get 1.37 seconds. Okay, next problem. We have let me remove the staple for the moment. Mass m is equal to 1.81 kilograms, connected to a spring, oscillates on a horizontal frictionless surface as shown in the figure. The equation of motion is given by x is equal to 0.287 cosine 1.79 t, where x is measured in meters, time t is in seconds. Determine the period of the motion. Okay, so let's just read off the easy things. X is equal to a cosine omega t. A is the amplitude, is 0.287 meters. Omega, here, if you read it off, is 1.79 radians per second. Okay, so to get the period is 2 pi divided by omega. That's 2 pi divided by 1.79, and we get 3.51 seconds. Now the maximum speed reached by the mass is what? Okay, the maximum speed, so that's a times omega. This comes from basically what they're saying is, all right, so you have this on your equation sheet that v is equal to, it's just the derivative of this guy, it's on your equation sheet, minus omega a sine omega t. The maximum possible value this can have, okay, is, pull out this factor here. The point is that the largest possible value, the minus times minus sine of omega t, this is the biggest it can be, is equal to 1. So the biggest that v can be, in other words, v max must be equal to a omega. Okay, a omega is so a is 0.287, omega is 1.79, you get 0.514 meters per second. Next one is to determine the spring constant. Omega is equal to the square root of k over m for a mass on a spring. So omega squared is k over m. Solve for k is m omega squared. And we get 1.81 times 1.79 for omega squared. And we get 5.80 newtons per meters. Next question. Consider a vertical spring with spring constant 24.63 newtons per meter hanging from the ceiling. A small object with mass 1.247 kilograms is added to the spring, and the spring stretches to its equilibrium point. The object is then pulled down and released. The speed of the object at a distance 5.921 centimeters from the equilibrium point is 4.552 times 10 to the negative 1 meters per second. How far was the object pulled down? Okay, so they are giving you a speed, they're giving a distance from the equilibrium, so we want to know the amplitude, how much it was pulled down in the beginning. So this is a conservation of energy problem. That's how we're going to figure it out. Okay. So notice the clues in this. They tell you the distance from equilibrium, they tell you the speed. That sorts of should give you some hint that this is a conservation of energy problem. Okay, the mechanical energy is K plus U, kinetic plus potential. It's 1/2 mv squared plus 1/2 kx squared. So we get 1/2 of the mass, 1.247, times the v, the speed, which is 0.4552 squared, plus 1/2 times the spring constant, that's 24.63, that's in the problem here, times the displacement. It's given in centimeters, so it's 0.0591 squared, and that comes out to 0.172 joules. Now, the mechanical energy is also equal to 1/2 k times the amplitude squared. This is not directly given in your equation sheet, but it's a useful formula. The reason why I believe it's not in your equation sheet is you should be able to figure it out just very simply, that the mechanical energy is 1/2 mv squared plus 1/2 kx squared. So when ax is equal to the amplitude, when it's stretched at the maximum point, this is when the velocity is equal to 0. And so as a result, we get that at that point, the mechanical energy is just only in the kinetic energy, and that's 1/2 Ka squared. Okay? So this is actually a very useful formula. It's not on your equation sheet, but you can just get that from the fact that mechanical energy is 1/2 mv squared plus 1/2 kx squared. And then when x is equal to a, v is equal to 0, it's stretched as much as it can stretch, and the speed is equal to 0. And so the mechanical energy is 1/2 kx maximum, which is a squared. Okay, so coming back to the problem, we have the total mechanical energy is 0.172 joules, and that's equal to 1/2 Ka squared. So now we can solve for a. We get a squared is equal to multiplied by 2 times mechanical energy to get rid of the 1/2, and then divide by the spring constant K. So we get 2 times 0.172 divided by 24.63, and we get 0.01397. And then take the square root of both sides to get 0.118 meters. Last problem. A pendulum has a period of 1.59 seconds on planet Ovid, where the acceleration of gravity is 11.5 meters per second squared. What is its period on the surface of Ovid's moon, Elsie, where g is equal to 4.025 meters per second squared? Okay, let's write down. So remember, if we're comparing, this is what happens on one place, this is what happens on another place. You could have a lot of problems like this on quiz 6, so get used to this. Label them separately. Ovid, the formula for the period on Ovid, T Ovid is 2 pi square root of L over G, small g Ovid. T Elsie is equal to 2 pi square root of L over G Elsie. Okay. Now, they want to know, they give you information about Ovid, they want to know about Elsie. So what I'm going to do is just take the ratio of the two, okay? T Ovid over T Elsie to try to cancel things out. So I plug in my formula for T Ovid, formula for T Elsie, and then the 2 pi's go away. Then I have the square root of this guy in the denominator. The denominator is in the numerator. This guy's in the denominator. So I get square root of 4.025 for Elsie, small g, and then divide by 11.5 for Ovid. And that comes out to with the square root comes out to 0.592. So we have the ratio of T Ovid over T Elsie is 0.592, but we want Elsie, so I need to cross multiply and divide by 0.529. So T Elsie is equal to T Ovid divided by 0.529. That comes out to 1.59 divided by 0.529. That's equal to 2.69 seconds.